In this video, I will talk about how we can use the center of mass to calculate angular momentum, kinetic energy, and potential energy. And I'm going to start with angular momentum. I have here a rigid 3D, if you want, object. And I have set a coordinate system with the x-axis, the y-axis 0, the z-axis goes out of the page towards you. And with the uppercase R, I'm showing what the center of mass is. So the vector R shows the position of the center of mass with respect to this frame of reference. Now, it is important to understand by definition, the angular momentum of a point particle is defined as the cross product between the vectors r and p. And if I calculate the angular momentum with respect to a point that I call point A, then this r is the vector that has the tail at the point A and the tip at the location where my point particle is. Let me draw a picture to show you what I mean with that. So if, let's say, I have a point particle here, and it has a mass and it has a momentum, then if this is my reference point, if this is location A, then the vector r will have the tail at my reference and the tip at the point where my particle is. Okay, so it is important to understand this is the definition of angular momentum for a point particle. Now, then you may think, so what do I do if I have a 3D, a solid object? Remember, we have done this process in the past. Anytime you have a solid object, you can always break it into a large number of small pieces, infinitely small pieces, that you can model as a point particle. And then for each one of those, so let's say I break this one into one point particle, another one, and so on. For each one of these, you can apply the definition of the angular momentum r cross p, and then whatever you get, you add all of those angular momenta to get the angular momentum of the entire object. Okay, let's erase this. So it is important, I do want to emphasize, this is the definition. Now, using the definition of the angular momentum and the definition of the center of mass, I can show mathematically, I'm going to skip the mathematical proof. I want to focus on what do I start with and what is the final result and what does it mean. So I'm going to skip the mathematical proof and I'm going to talk about if I do this, if I use a definition, of the center of mass, and I break the solid object into a large number of small pieces, and I add all of those angular momenta, then I can show that the total angular momentum of the solid object, let's make some notes. So this is the total angular momentum. This can be written as two terms, as the angular momentum of the center of mass that we call the L translational, the translational angular momentum, and another term that we call the spin or the rotational angular momentum. So this is the rotational or spin angular momentum that essentially describes the rotation, the motion of the solid object around the center of mass. All right. So if you want me to calculate the total angular momentum of a solid object, I'm gonna do it by looking separately into the two components, the two terms of the angular momentum. The translational angular momentum, which will be the angular momentum of the center of mass, and the spin or rotational angular momentum, which essentially is the angular momentum relative to the center of mass. Now, why are we doing this? Well, do we have to do it? No, I don't have to do the calculation this way. If I really want to, I can always use the definition of the angular momentum, and whatever I do with this, my calculations will end up at the same result as doing it this way. The difference is, if I always use the definition every time I have a solid object, it's gonna take me a ridiculous amount of time to find the angular momentum of the solid object, and I don't want to do that every single time I need to work with a solid object. So the only reason we use mathematics to turn this and the center of mass into an expression that looks like this is that at the end of the day it makes our calculations much more efficient. But there is no new physics really included here. Now, something similar is we can do with kinetic energy. So if you ask me what is the total kinetic energy of that solid object, then I can say, well, I'm going to calculate it as the kinetic energy that we call the translational kinetic energy plus another term that we call the EK rotational. Now, what is that? So the term on the left, this is the total kinetic energy of the solid object. This is the translational kinetic energy, that is the kinetic energy of the center of mass. Okay, so to calculate this quantity, I assume I have the center of mass here with the mass equal to the entire mass of the solid object, and then I calculate that as the kinetic energy of a single point particle. Now, this is the rotational kinetic energy or spin, if you want. That is the kinetic energy of the solid object around the center of mass. Okay, again, it's the same idea. Do I have to use this expression every time I have a solid object? No, I don't, but it does make my life much easier. My calculations are much more efficient if I do it this way. And the last thing that I want to talk about is the potential energy. If before I get to that, I do want to remind you, the potential energy is always due to interactions. Okay, so by definition of the concept of potential energy, this energy is associated with interactions between two objects of our system. In contrast, the kinetic energy is associated with the motion of an object of our system. Here, potential energy is associated to the interactions of our system. Now, if our system, okay, let me give you an example. If my system includes a solid object but it also includes the Earth, then the potential energy of my system will be due, in this case, will be due to the gravitational potential energy between the object and the Earth, and it will also be to any interactions that a particle of our object has with the other particles within the object. Let me show you an example here. So let's say this is my solid object, okay, and I have this particle here, and let's say that it has, let's say it is a simple atom, and let's say that it has a chemical bond, which I illustrate here with the spring. Okay, the spring is a chemical bond or a bond. But also, I have the Earth. So let's say here, okay, this is the Earth. Now, there is a gravitational interaction between my solid object and the Earth, but also there is an interaction between those two objects. So I will have a gravitational potential energy because my solid object has a gravitational interaction with the Earth, but also I will have a potential energy associated with the interaction between the two atoms. Now, if this is not a chemical bond, but let's say you got a cation and an anion, then the nature of that interaction will be purely electric. So you got an electric potential energy of two particles within the object, and then you also have the gravitational potential energy between the object and the Earth. So going back here, this will be, you will have interactions, potential energy terms between the object and other objects within the system. Okay, when you use energy, and in particular energy conservation, you have to define what your system is. Whether you use Newton's second law, angular momentum, torque, energy conservation, you have to define your system. And whenever you calculate the potential energy of a system, then you can calculate that as a sum of two terms. The potential energy of interactions that your solid object has with other objects, like the Earth, within the system, plus the potential energy term that is about the interactions that occur of particles within your object, because those are also part of your system. So if here, okay, if I define my system to be the object, the solid object, and the Earth, then to find the potential energy of this system, I have to take into account all the interactions. This is one of them, this is another one. You may have an electrical interaction between two particles here that belong to the Earth. You may have interactions here between those two particles and between those two particles. Okay, if those are conservative interactions, then you have to include them in your potential energy. So this is what the second potential energy term illustrates. I do want to mention, I do want to make a connection between this and how we use energy conservation. We probably have seen this in the past. If you think about how many particles, how many atoms a solid object has, how many atoms, how many particles the Earth has, it is a huge number of particles. It is practically impossible to know the interactions and the potential energy of all pairs of atoms within a solid object. So typically, what we do typically, because this is so difficult to measure, and I would say practically impossible, okay, so difficult, but I would really say practically impossible to calculate or measure, we typically move this to what we call the internal energy of the system. And you probably have heard me in the past talk about this, especially in collisions. So, because this is so difficult to calculate, this is something that we often move it to what we call not K to what we call the internal energy of the system.